Here we have the expression for the nth multiple moment, which is given by the symbol xi. It has superscript n standing for nth moment, and there are n subscripts alpha, beta, all the way until nu, and alpha, beta, etc., all the way until nu. These are the components which take the value x, y as z. And on the right side, we have minus 1 to the power n over n factorial, and the summation is over all particles, electrons, and nuclei. If the system is a molecule, qa is the charge of eighth particle, ra is the position of eighth particle to the power 2n plus 1. And you have n partial derivatives with respect to the position component alpha, beta, all the way until nu, and we are going to differentiate 1 over Ra. So we are going to verify this relation for the special case of n equal to 1. So we know that when n is 1, we have the first multiple moment, which is the dipole moment, for which we already have the more familiar expression, which I'm going to put inside a box. So we're going to start with the general expression and substitute n equal to 1. And we're going to verify whether this expression is the same as the more familiar expression for the dipole moment operator. So we will start by doing this part, which is going to give us dou by dou r a alpha of 1 over Ra, which we are going to write as Ra to the minus 1, which is going to be minus R subscript A to the minus 2, and we are going to apply chain rule and differentiate with respect to the alpha component, the function. So we are going to substitute here the more familiar expression of distance equal to square root of x square plus y square plus z square, which is the length of the vector. So we will have negative 1 over Ra square dou by dou Ra alpha sum over, I'm not going to use alpha, I'm going to use beta, so I'm going to use another dummy index. The reason is we already have an alpha here, so we don't want to differentiate with respect to something where you again have alpha, so I'm going to use a different dummy index beta, or a beta square over 1 by 2. So this will give us negative 1 over Ra square 1 over 2 summation Ra beta to the 2, and we'll have to do n minus 1 as the power, so this is 1 by 2 minus 1, so this is minus 1 by 2, and we will have to apply the chain rule, so we are still left with dou by dou Ra alpha summation beta Ra beta to the 2. Okay, so what do we have? We have negative 1 over Ra to the 2 and 1 over 2, and this is just 1 over R, okay, because this is Ra, so this is 1 over Ra, because you see the power here it is half and here it is negative half. So we are going to just write it as 1 over RA, and this derivative is going to survive only when beta takes the value of alpha. Okay, alpha is either x, y, or z, and beta will go over x, y, and z. So when the value of beta and alpha are the same, the derivative is going to survive. So we will have 2 RA alpha to the 1. So I'm just going to leave out the 1. So now we can cancel out a lot of terms. 2 is going to cancel, and then this RA and then this RA square can combine to give us a cube term. So we will have negative RA alpha over RA cube. So now we can substitute this term over here, and we will get xi operator 1 alpha equals negative sum over a qa RA to the 3, and here we have negative RA alpha divided by RA cube. So the cube term cancels out and the negative sign cancels out, and then you have sum over a qa RA alpha, which is the same as the expression that is given in the box here. So this is the same as mu alpha operator.